I guess this must be, since it's coffee filters, must be what Professor Jacobson showed to you last Thursday, which is okay. I probably can guess what you meant. So this was about demonstration with coffee filters. I haven't had a chance to look at what Bob exactly showed. The videos has just been posted online. My guess is the demonstration looks something like this. So the question was, Bob showed a demo with coffee filters. I do not have coffee filters, I have pieces of paper. So Newton's universal law of gravity says that all objects fall in Earth's gravity with the same acceleration of g of about 10 meters per second squared or 30 feet per second squared. But it contradicts your everyday observations, in a sense that if you drop something heavy, and I'm looking for something heavy, like this object. If you drop something, I hope not to break it. If you drop something heavy, it does fall with a fairly significant acceleration. If you drop something light, quote unquote, it falls slowly. And if you take actually even an object of the same mass, but different shape, this falls quicker than that. So this is probably something similar to what Bob showed with coffee filters. So this seems to violate the laws of gravitation, except that the law of gravitation, I think Professor Jacobson probably showed you another demo, which had an evacuated jar with a feather and a piece of aluminum, right? So what it says is that the universal law of gravitation only talks about gravity. It does not talk about air resistance. And so it works in idealized conditions of being in vacuum. If air resistance is negligible, if you're out in space. You guys seen the movie Gravity? Well, it should have been actually called inertia, to be honest. Most of the effects were, except for the last piece where she's falling in the Chinese spacecraft to Earth. Actually, almost everything else did not have anything to do with gravity, but with inertia. I especially liked this part where she had to throw a wrench to propel herself. Conservation of momentum actually works in space. So that's an aside. In space, if you're out there, air resistance is negligible. Every object would, in fact, fall, or rather experience gravitational force that's universal, independent of acceleration, would be independent of mass. So if you were actually on the orbit and not moving around continuously, but if you're actually sitting just there, you'll be falling towards the Earth with the acceleration of roughly 10 meters per second squared, slightly less because you're farther away from the center. But we on Earth, luckily, don't have vacuum. We breathe air, and air, it adds additional force. And that force depends on the area. So, for example, that's one of the reasons if you watch Olympics, not the Winter Olympics, but the Summer Olympics, you see bicyclists in this very air dynamic helmets. It reduces the area and also reduces the turbulence, reduces the drag. All of their resistance effects are proportional not to the mass of the object, but to the area, and and they also depend a little bit on the shape. So objects of the same mass, like this one, has an area that intersects the air column that's much smaller than this. And so the force acting on this little piece of paper from air resistance is significantly larger. The gravitational force is the same. Air resistance is much larger for the big object, and therefore the net force that propels this object downwards is much smaller for this than for that. Basically, gravity is the same, but you're subtracting off air resistance from both of them. Air resistance is larger here, so the difference between gravity and air resistance is smaller for this object than for that. And therefore, they fall with different accelerations. But the universal gravitational law, if I were to put both of them in a jar and evacuate it, they would fall with the same acceleration. Does it seem to answer? Okay, not quite. Okay. Do you guys have any other? I'll come back to coffee filters. Again, later today, there's a story about coffee filters that has to do with radiation and Fukushima fallout. And actually, Professor Jackson was involved there too. Let me see, do you guys have any other questions? So let's switch to the projector, to that screen. We're already there. What you see is a device called the cloud chamber. It's a volume of oversaturated vapor. In this case, it's alcohol vapors. Oversaturated means that this vapor is just about to become liquid. It's in a state of pressure and temperature where it's just about to condense. But it doesn't condense unless there are condensation centers, unless there are some impurities in this gas around which some ions, around which the clouds would start to cluster and form. So if a charged particle passes through this chamber, it will create those ions, those clusters of ionization, and the pattern of that cloud will tell you where the particle went, where the energy was deposited. I'm looking for my... So now, unfortunately, we don't have a radioactive source, so you have to look quite carefully at cosmic rays. So kind of watch this. Okay, now it's... So here's the bubble, or rather cloud. Here's the cloud. Here's a very nice track. This is a cosmic ray. This is a cosmic ray. This was a very short track, and the thickness of this cloud and the length of the cloud tells us something about what kind of particle it was. If you see a very long track like this, it means that the particle actually went all the way through, so it had more energy than the particle that deposited a relatively short track. Also, the thickness tells you about how many ions per unit area is created. So long particles are probably segments of cosmic rays that pass horizontally. And when you see a cloud that's shorter, it's probably a particle also that's going at a steep angle, and also perhaps, or a particle that loses energy more quickly, a heavier object like an alpha particle. So this is a very visual device to tell you that about direction, energy distribution, but just about the presence of radioactivity. All of these events are created by natural radioactive sources, either cosmic rays or, in some cases, radioactivity on the glass. You know, all materials around us are slightly radioactive. You're full of potassium. There's this uranium and thorium that's in the Earth's crust that contaminates pretty much everything around us to some degree. Uranium and thorium produce alpha particles. They stick to glass and can decay and deposit energy into the cloud chamber. So again, this is a very visual way to demonstrate radioactivity. If we had a source nearby, which we had trouble with sources on Thursday, well, let me do an experiment. I'll actually take a, let me take a strontium source, which is a source of beta rays. Stick it on the top. Probably turn the lights off. Not much happens. These beta rays have trouble penetrating all the way down. Let me try gammas. So the gamma rays from the source will exit in all directions. gamma rays don't produce enough ionization by themselves to actually see as a cloud, but they may interact with an electron in the chamber every once in a while, and this electron would be highly energetic and would produce a cloud. So this, unfortunately, what you look at it is from the top. So most of these events will deposit energy around it, but would be directed downwards towards the cloud chamber, so you see them sort of sideways, kind of from the top. But you should see events that kind of point towards the source. These are gamma rays that interact with a material in the cloud chamber producing electrons, basically knock electrons out of the atoms, and then you see a track from an electron. All right. So now that, can we switch to the computer screen, please? Let me close everything so that my computer doesn't die. This is a, oh, it would help to connect. We talked about the typical units of radioactivity, in particular, units that tells us about activity. These are these units, becquerels and curies, which measure how often a nuclear decay happens from a particular source. Becquerels are a little bit more easy to understand units, because it's basically a unit of 1 decay per second, 1 process a second, so it's kind of easy to count in human countable units. 1 becquerel, 1 decay per second. Curie, on the other hand, is a more conventionally used unit when you discuss radioactivity. Sources like this, in units of becquerel, are highly active. These sources have activity of microcuries. So the strontium source has an activity of 0.1 microcurie, cobalt-60 as well. 0.1 microcurie, so micro is 10 to the minus 6, 1 millionth. This is 0.1 of that, so 10% of that, so 10 to the minus 7. Curie multiplied by this conversion factor, it means that these little sources produce over 1,000 decays a second, or roughly 4,000 decays a second each, all going in all directions. So even a small, and this is a relatively weak source, something that we can actually, buy legally and get shipped by US Postal Service and delivered here on campus. If your smoke detector has activities of similar scale, actually a little bit higher. So the point being here is that even a small amount of radioactive material produces a lot of decays per second, and so we usually measure the activity in these composite units with a large exponent, microcurie or millicurie. But what's important for humans is how much biological damage a given source of radiation produces, and so that depends on what type of radiation we are dealing with. We are talking about gamma rays that penetrate relatively far. You saw that I was able to place a source on the top of the chamber and it would penetrate through the entire chamber, and you can see a short track. Alpha particles get stopped by effectively a thickness of your skin or a piece of paper. And beta particles, electrons, are somewhere in between. They typically penetrate in air. The distance scales are a few millimeters. That's, you saw those tracks, millimeters. So in material, they would be shorter. So what it means is that as particles that deposit more energy per unit length can do more damage to your cells per cell, and therefore may have a higher chance of either causing radiation, poisoning, sickness, or causing long-term effects such as cancers. And so particles that deposit energy locally, the heaviest particles, alpha particles and fission fragments, are most dangerous per unit of activity, and gamma radiation is less sensitive. On the other hand, gamma radiation is more difficult to protect against. You need more material to shield against it. So I showed this towards the end of the class. The typical units, we measure the amount of impact radiation makes on a human in these units of RAMs or sieverts, which tell you, these units, which tell you how much energy is deposited per kilogram of the body, and then multiplied by this coefficient that describes the biological damaging effects. So this coefficient is defined to be 1 for gamma rays, and it's larger than 1 for everything else, and for the alphas it's also depends a bit on energy, but it's sort of on the order of 10. And so if you want to reduce your exposure, you need to know what kind of radiation you're dealing with. If you want to reduce exposure to alpha particles, well, don't swallow them. Alpha particles get stopped by the thickness of your skin. Skin regenerates, right? You have dead cells on the surface. You shed them, the skin grows back. So damage to the skin is relatively easy to repair. Damage to the liver is relatively hard to repair. And we'll talk about what happened to Mr. Litvinenko in a second. At the same time, we saw from the cloud chamber that radioactivity is all around us. We are constantly bombarded by cosmic rays. We breathe radon-infused air. Radon is a byproduct of uranium-thorium decays. So it's a byproduct of natural radioactivity. Uranium and thorium are normally located in the Earth's crust, but also, you can pick it up in a rock. Radon is a gas. Radon is here. Radon is in the same column in the periodic table as helium, neon, argon, krypton, and xenon, and those those are all gases. Helium, in particular, is a gas you get in balloons. So if radon is produced in uranium decay, it will eventually become a gas and it will bubble to the surface. So in the normal atmosphere, there are actually natural radioactivity from gaseous radon that can actually be fluid. That's a significant part of your yearly radiation dose, is exposure to radon, and that also varies significantly depending upon whether you live in a swamp, or whether you live in the rocky terrain, or whether there are cracks in your basement, for example, which can stimulate the emission of the gas a little more. If you somehow have to undergo a medical procedure for a CT scan or an X-ray, you experience radiation as well. And in fact, if you do a head CT scan, CT stands for computed tomography. We'll talk about how that works later in the semester, but basically it's a series of X-rays. A large number of X-rays gives you a three-dimensional picture of your brain or any other object, but since it involves a large number of X-ray shots, the radiation effects compound. And so you get up to 200 millirem, which is about a half or more than half of the typical yearly dose an average human receives. If you're a pilot and you fly a lot, or if you travel quite a bit like me, you get some more exposure through the cosmic rays, from being up elevated above most of the atmosphere, and therefore being bombarded by cosmic rays without significant protection from the Earth's atmosphere. So there's actually, I can put another link here. There's this link to XKCD cartoon that gives you a pictorial view of various doses from various radiation sources. There's also a website where you can type in and compute your typical exposure per year depending on your lifestyle and where you live. You know, if you live in Denver, you'll get a little bit more from cosmic rays, and also it's exposure to granite and rocks. And if you fly a lot, you can account for that too. If you undergo medical procedures, you can account for that as well. So I computed my exposure last night, and it's slightly higher than this, basically due to the fact that I tend to fly to Europe several times a year. It's about 450 millirem. So how dangerous is this? Well, there are two effects of radiation on the human body. Two effects that have already obviously been observed. Two effects that can cause harm. One is, so again, the reason that radiation causes harm is that it changes chemical and therefore biological processes in your body by changing the atomic structure of the elements in your body. High energy ionizing radiation passes through. It knocks out electrons. Usually, most of the time, it will knock out an electron from an atom. It can do it to many atoms in your body, in the cells. It typically deposits roughly, cosmic rays, for example, deposit roughly 2 mega electron volts per every centimeter of the body. So, and it only takes 1/1,000,000th of that to separate an electron from the nucleus. So a given cosmic ray can produce up to 1,000,000 ions as it passes through. Gamma rays like this can produce the same thing too, can separate up to 1,000,000 ions as they pass through your body. And the only difference between cosmic rays and, say, alpha particles, how densely those ions will be populated. Alpha particles will deposit everything locally in a single cell, and betas and gammas and muons may spread that deposit around. So, you know, 1,000,000 ions per single particle is the story. So how dangerous is this? Well, cells, well, humans, obviously biological objects, have an ability to regenerate. That's the good news, right? You know, we shed our skin and then it grows back. Hair grows back when it's healthy. Cells have ability to repair themselves. However, if the damage is too severe, then the cells may die before they are able to regenerate themselves, and therefore the biological effect will occur. So once the ions have different chemistry from the neutral atoms and molecules, and therefore chemistry changes. If that change is localized and affects a large number of cells, you'll start feeling the effects. So here are the typical numbers. Remember, your normal dose, radiation dose per year, is about 3 to 4 millisieverts per year, or 3 to 400 millirem. The dose where, and you know, most of us live healthy lives and don't feel the effects on the scale of 3 to 400 millirems. If you receive doses of roughly 1,000 times larger than this, 3 to 4 millisieverts as opposed to 3 sieverts or so, you will start feeling significant effects. So 3 sievert is so-called LD50 dose, which stands for a lethal dose at 50% probability, if untreated. So 3 sievert or 300 rem is about 1,000 times larger than your natural dose that you receive per year. 3 sieverts deposited in a short period of time. So this is known as acute dose. Doses about half that much are significantly noticeable. You know, I'm sure people who receive radiation treatment for cancers, some of you might have experienced that yourself. The symptom of radiation treatment for cancers is nausea, hair loss, but if radiation treatment is successful, people recover. So the typical doses people receive in cancer treatment are about a sievert. So clearly, this is a produce significant biological effect, but this dose, one can recover from this dose. Doses of the order of 3 sieverts are often lethal, and doses of the order of 10 sieverts or 1,000 rem are certainly lethal, that a person is unlikely to survive. So again, this is about 1,000 times more than your typical dose per year. So there clearly have been many examples of this. So these doses are known quite well because unfortunately we have actually observed people receiving such doses, either after Hiroshima and Nagasaki, or in specific either accidents or when people receive these doses deliberately. You may have heard the story about Alexander Litvinenko. Well, he died in 2006, so that's 7 years ago, so you were still teenagers. You may or may not have heard the story on the news. He was an ex-KGB spy who escaped the long arm of the KGB. He lived in England. He was a bodyguard for some Russian oligarch. They had some falling out. So there was some tension between them. Plus, he also started telling stories about Putin. So he was kind of an inconvenient person to be around. At some point, he went out to a Japanese restaurant to have sushi, to drink some tea. He met two other former KGB, or actually FSB, the new Russian service agents there. They ate, they talked. He met some other guy from Italy, also former spy. They ate, they talked. And a few days later, he fell sick. This is him on his deathbed. So as it turned out, further analysis determined that he was poisoned by polonium-210. Polonium-210 is not a naturally occurring isotope. Polonium-210 has to be produced. Polonium, well, it was discovered, polonium is, the root is Poland. Polonia is the Poland name, so I guess it probably means it was discovered by Marie Curie. It's an element in the periodic table. It's slightly lighter than, it has a atomic weight of 209 for a stable isotope. So it can be produced. The normal polonium is not dangerous, but if you add another neutron to it and make polonium with the atomic number 210, the element becomes highly radioactive and it emits alpha particles. It decays by alpha decay, producing this very energetic, short-ranged radiation particles. So, if you handle polonium and, typically the energy doesn't penetrate your skin, but if you ingest polonium, it's here in the periodic table above tellurium, selenium, and sulfur. So it basically chemically behaves like sulfur, and your body tries to get rid of it. Polonium is actually dangerous for two reasons. Well, if you know anything about chemistry, tellurium and selenium are kind of nasty substances too. Well, sulfur isn't that pleasant either. There are jokes about chemists who work with selenium and tellurium. It smells like rotten garlic. The jokes are if a chemist who works with selenium walks onto a bus, everybody else leaves, except for a chemist who works with tellurium. They can sort of fight each other. Polonium itself is actually poisonous in large doses. But the worst thing is that if you make a radioactive version of it, polonium-210, your body will try to get rid of it. The natural filter in your body is liver, so it gets deposited into your liver. And there it sits decaying many times a second. And the energy from radioactive decay gets deposited directly into your liver because the alpha particles don't travel very far. So pretty much every radioactive decay does damage to one vital organ in your body, the liver. That's what happened to Mr. Litvinenko. He received a dose of more than 1,000 rem. Clearly, it was an overkill. Well, 1,000 rem is lethal. He received clearly lethal dose, but even more importantly, that dose was not even spread out over the entire body. If you receive 1,000 rem spread out over the entire body, it's lethal. He received it all deposited into the liver, and that cannot be recovered from. Now there's, the guy met, at least 3 spies. His boss was unhappy with him, so there are debates about who actually poisoned the guy. Of course, the British intelligence blames Russians. The Russian intelligence blames Italians. It's actually still not clear, but it's clear how the poison was delivered, through the tea. Strangely enough, small enough amounts were delivered so that he couldn't taste the rotten garlic smell and taste in the tea. Not a nice way to go, by the way. So these are examples of radiation damage that can be very visible very quickly in, and this is one example. I recently read a story that traces of polonium-210 were found in some other instances of high-profile politicians. Yasser Arafat, right, is the Palestinian leader. There were stories about traces of polonium found in his remains that are not substantiated. He was relatively old, I think. So the official story is he died of natural causes, but there are disputes, especially by Palestinian authorities. So as it turns out, at least after this incident, polonium-210 becomes a relatively infamous source. So it's time for a quiz. Pull out your remotes. Of course, what happened in the other example of people receiving high doses of radiation is Chernobyl. Let me start my software. What I would like to ask you is what you know about Chernobyl. Okay, there's an issue with my clicker. Okay, give me just a sec. There's my software tells me that I need to enable my network, otherwise UI clicker goals will not work, so give me just a sec. In the meantime, you can think and perhaps Google if you wish. Question is about the biological effects after Chernobyl. And then we'll discuss how much radiation typical people received in Chernobyl, but the effects are clearly measurable. So let me start. Are you guys ready? Let me start the poll. And I'll give you about a minute. Okay, 5 more seconds. All right, let's stop here. Look at the results. Well, okay. 81% of you think 5 to 25,000. That's the right answer. Now the question is, was this acute or was this long-term? Let's look at the effects of radiation again. Where am I? There is a, in addition to acute doses, so in fact, yes, there's a reason there's a very large range here. This is the officially quotable death toll, and it has a range of a factor of 5. Clearly, if these were acute, if these fatalities happened relatively soon after the accident, one would be able to count. The main reason for this uncertainty is that this actually is not a directly attributable effect. It's a calculation based on this graph. Based on the graph of how much extra cancers can be generated for a particular radiation exposure. This is the entire data set. So the typical number quoted very often, quoted in Professor Muller's book, you can find it on the wiki with a similar orders of magnitude. The typical number for the rate with which the chance of excess cancers increases per unit of the radiation dose in RAM is 100% increase in the rate of cancers per 2,500 RAM, spread out over the population. Now, there are two ways to understand this number. First of all, what does this actually mean? Does it mean that if you receive 2,500 RAM, you have a 100% chance of getting cancer? The answer is actually no. If you remember, the lethal dose is 1,000 RAM. So if somebody receives 2,500 RAM, they're not going to get cancer. They will be dead before. What this number means is that this is the extra cancer chances when this amount of radiation is spread over the population. Then you can count how many people have actually received an extra cancer per capita. So 2,500 RAM spread out over 2,500 people will generate one cancer. In 2,500 people. If you spread this dose over, say, 25,000 people, there will be one cancer for 25,000 people. So this is so what you probably care about is what is your chance of receiving cancer for a given radiation exposure. If you're exposed to radiation, let's say if you lived near Hiroshima and you received 140 RAM, that's roughly 50 times more than a typical annual dose a normal human receives who doesn't live in Hiroshima right after the bomb. So that's effectively equivalent to 50 years of exposure. What is the chance of receiving cancer? It's 6% above the normal rate. Do you know what the normal rate is? Normal rate is about 20 to 25%. That's actually extremely significant. I mean, that's a scary number. If without any medical advances in cancer treatments and cancer detections and perhaps in curing cancer, 1 in every 4 or 5 of you will die from cancer. So look around. 1 in every 5 or every 4. It's a significant number. Of course, most of these cancer deaths are not caused by radiation. Most of these cancer deaths are caused by sources that we don't quite understand. It may have to do with your lifestyle. If you smoke, your chances increase. If you drink, your chances increase. Well, you know, if you live and breathe pollution, if you live in a house that has asbestos, your chances increase. We don't quite understand all of the mechanisms that cause cells to misbehave, to be honest. This is an ongoing area of research because it affects every one of us. It will affect ultimately every fourth person in this room, and therefore it will affect somebody in your family, it will affect somebody you know. So cancer is a big deal. That's why there's a lot of research in both causes and cures. Relative to that rate, 25% of every human on Earth will die from cancerous causes over their lifetime. Over the average lifetime of a human, that's probably integrated over the entire population of the Earth is probably on the order of 50, 60 years. Much better here, 80 or so years in the US. Integrated over that, there's 25% rate. So to reach that level, to double that rate, you need to receive extremely high doses. Right? Extrapolate this plot up to about 25%, and we'll be talking about actually nearly lethal doses. So at relatively low levels, the cause and effect of radiation is much less clear. And the main reason for this is that it's very difficult, when the overall cancer rate is 25%, it's very difficult to actually identify a particular human and tell for sure whether they've received the cancer because of the extra radiation they've received or because of something else. I'll give you an example. Anybody of you live in Marin County? All right. You know the stories. Especially important for women, the breast cancer rate in Marin County is higher than average in California by about 15%. There are reports that maybe it's been going down recently, but sort of over the last 10 years, integrated, the average cancer rate in Marin County is higher than elsewhere in California, about 15%. And the California rates are a little bit higher than average in the country. Does Marin County receive more radiation? No. Well, there are areas that are slightly elevated, but the typical radiation exposure is about the same. It's not particularly dirty. I don't think there are power plants or, okay, there are refineries, but they're sort of farther away in Contra Costa County. So it's not actually clear what effects cause that. There's research ongoing, and it may have something to do with the fact that it's slightly more affluent on average community than the rest of the Bay Area, so therefore screening rates are actually higher. That may be part of the effect, but probably not the actual cause. Obviously, it's a correlation, but not causality. It may have something to do with the lifestyle of the population. But given that we don't understand these high rates, and the rates are high, it's very difficult for low levels of radiation. It's very difficult to determine what happens if you receive small but non-zero dose of radiation above your natural background. Again, a couple of other examples. Denver actually has a lower cancer rates than average in the country. And again, it's not clear why. People living in Denver receive higher dose of radioactivity than the rest of the country on average. They live at the elevation of about a mile, so their cosmic rates are higher, but also they live in the Rocky Mountains, and the radon rates are a little bit higher. They receive about 20% more dose per year than everybody else on average in the country, and yet their cancer rates are lower. So does it mean that receiving low rates of radiation is actually good for you? No. Well, the answer is we don't know, actually. The answer is that at these low levels, it's very difficult to be scientifically accurate. There are actually other examples. There's apparently a city in Iran called Ramsar. It's also kind of in the mountains. The radon rates are really high there. People receive about 200 times more radiation per year than elsewhere in the world, and yet again, cancer rates are lower. Again, does it mean that radiation is good for you? It's not clear, because there are other effects that are probably changing the cancer rates in those particular locales that are significantly stronger than the radiation. So what you see is that there are 3 plots here. In fact, all of these 3 plots are feeds to the same exact data. The data comes from observing people in Hiroshima and Nagasaki who received very high radiation exposures, very high being in the units of hundreds of rem. And so for these large exposures, one can actually count. One can look at people in the neighboring cities in Japan, compute their typical cancer rate, and subtract it off from cancer rates of Hiroshima and Nagasaki survivors, take the difference and correlate it with the amount of radiation exposure they have received, which can be measured. And that's the only scientifically available significant data set. And so I can describe this plot, this dependence, with several hypotheses, with several possible graphs for how radiation affects the body. The standard one is so-called linear no-threshold hypothesis. It basically says that no matter how small of a dose, radiation dose you receive, it will cause an increase in the average cancer rate. So that's the statement that no amount of radiation is safe, and any amount of radiation will cause an additional increase in the cancer rates. So-called LNT, linear no-threshold hypothesis, and the numbers are this. One, doubling of the rate per 2,500 rem of exposure. And so if your exposure is, let's say, 1,000 times less than 2,500 rem, so that would be 2.5 rem, roughly half of the annual dose allowable to radiation workers in the US, your chance of getting a cancer would increase by 0.1%. That's the calculation. But of course, there are other options. Well, maybe the dependence is actually stronger than linear. Perhaps higher and higher radiation dose will cause more and more kind of accelerated damage. So I can try to describe this graph by a so-called quadratic, second order, faster dependence. And so it's this blue dashed line. And you see it kind of becomes steeper as we go out. But there's very little difference between the red and the dashed. And then there's also a black line, which you can see on this graph, which is so-called linear with threshold. This is how it looks. The natural dose of radioactivity is here, by the way. So here's how the linear with threshold hypothesis looks. It's something that I completely made up. There's no scientific evidence for either to discriminate between this one or that one. But this is how linear hypothesis with threshold would look. You can make an assumption. Suppose everybody in the US, or actually as elsewhere in the world, on average, receives about 300 millirem dose of radiation. So we all live with it. So perhaps that's a natural dose. Perhaps that's something our bodies have been accustomed to and can recover from. So suppose any radiation below that level doesn't do anything at all to you. Perhaps cells have a chance to recover. And then radiation above this limit causes a linear increase in cancer rates. It's a hypothesis. We can test this hypothesis by looking at the data. And you can see that both this graph and that graph describe the data exactly the same way because the data is taken at much higher exposures. There's no way to tell the difference. So at this very low level, the behavior is very different. But we cannot tell the difference. So when you hear statements about this, you have to take them with a grain of salt. If people make statements and say, no amount of radiation is safe, or when people make opposite statements, that slow amounts of radiation are actually good for you. Neither of those statements are actually based in science. They are hypotheses that are extremely difficult to prove because we have basically no data that can correlate extra cancer rates to radiation exposure at these very low levels. We'll be talking about increases in cancer rates on the level of 0.05%. And given that 25% of people will receive cancer and there are large fluctuations given by lifestyle and locales, it's extremely difficult to measure. So take it with a grain of salt, the statements that people make. If somebody is extremely sure about either this graph or that graph at very low levels of radioactivity, they're either confused or they're lying to you. Okay, so what happens, of course, how do you receive large radiation doses? Well, if you don't work at a nuclear reactor, don't live near a nuclear weapons test site, you can still be exposed, and you can be exposed to radioactive fallout from any accident or to radioactive fallout from a weapons test. And those are the three main isotopes that will affect people who live far away from the site. The way most people get exposed to radiation from nuclear fission is by coming in contact with an isotope that's relatively easy to transport, so something that can be airborne, and an isotope that lives a significantly long time. So there are three main radioactive isotopes. Iodine-131. Where's iodine? Iodine is here. We all have iodine in our bodies. The thyroid gland accumulates some amount of natural iodine for bodily functions, which, to be honest, since I'm not a biologist, I don't understand very well. I know for a fact that iodine accumulates somewhere in the thyroid gland that's sort of here somewhere. There is a radioactive version of iodine, iodine-131, that lives about 8 days. Well, it's half-life of 8 days, so that means the amount of material is reduced by a factor of 2 every 8 days. So 8 days after the nuclear accident, there may be an amount of iodine in the air, and that amount is reduced every 8 days by a factor of 2. So iodine-131 is most dangerous right after the nuclear release. So let's say 8 days after Fukushima, there was rain here in the Bay Area with the clouds that came from the east. And so there was some amount of radioactive iodine in that rain. I actually tried to find it. I went outside, I filled out it was raining hard. I have a few radiation detectors in my lab. We went out, I filled a glass with rainwater. I put it in front of the sodium iodine counter. Sodium iodide is a scintillation detector that can count radiation. I couldn't see any traces of iodine-131 or cesium-137, but our friends at the nuclear engineering department here on campus at Chivery Hall had better detectors. They had germanium detectors. They collected much more rainwater than I did, not a cup, but literally liters and liters, and they could actually see traces. They were one of the first departments on the West Coast, actually in the US, that could see traces of radiation from Fukushima in minute amounts, in becquerels per liter, and I'll get to that in a second. They also saw cesium-137 and they saw strontium-90. Cesium-137, cesium is here, is a alkali metal, is similar to potassium and similar to sodium. Sodium is a natural salt. Potassium behaves also similarly, can be accumulated in the body, and so cesium can be absorbed as well, can also be airborne. And it lives 30 years. It dissolves in water as well. So just like salt dissolves in water, cesium iodine will be dissolved in water, and cesium ions can be carried by either oceans or rainwater. So one can absorb it. And since it lives 30 years, the amount of exposure doesn't decay very quickly. In fact, remember I showed you this plot last time? The fact that French wine is radioactive? Well, California wine is radioactive too. If you buy a wine bottled in 1965, it has up to 1 becquerel per liter of cesium-137. What does it mean? It means that in a bottle of wine, which is roughly a liter, 750 milliliters, there would be 1 radioactive decay per second from cesium. If the wine was bottled in 1965. But this radiation decays relatively quickly. As you can see, the amount of activity decays with a fairly short, well, with a lifetime of about 30 years or so. Do you know what this blip is? This blip is Chernobyl. This blip is, well, this blip and this blip is cesium-137 produced in nuclear weapons tests. Most of the nuclear weapons tests in the 60s were done at high altitudes, so that actually increases the amount of radioactive debris spewed in the air. Most of the radioactivity that we see today from elements like cesium are from those tests. And some amount was also released in Chernobyl. Chernobyl was the most terrible nuclear accident at nuclear power plants, and it still released roughly 20 times less activity than nuclear weapons testing. That's one of the reasons we don't do nuclear weapons testing anymore, or at least we have agreed with countries like Russia to not do them any longer. All right. And I guess the last, we're talking about dangerous isotopes. The last isotope is strontium-90. Strontium-90 is one of these guys. So this green peel is filled with small amounts of strontium-90. Is again, a radioactive isotope emitting beta rays. It also has a 30-year lifetime, half-life. Strontium is in the column just under calcium. So chemically, it behaves like calcium and magnesium. You know, you can take magnesium as part of your vitamin regimen. Calcium is good for the bones. Strontium became similarly chemically to calcium, so it gets accumulated in the bones. So if you eat fish, and a fish has been swimming near Fukushima plant, it probably has accumulated some strontium, and it will take that fish about 30 years to get rid of half of it. So, you know, after an accident, there was significant concern about fish from the west coast of Japan that could have extra amount of radioactively fissionable material like strontium. Or there was also concern, also after Fukushima and after Chernobyl, about milk accumulating some amount of strontium and calcium because of cows who are grazing on the grass not very far away from the fallout sites, and strontium accumulating in the calcium-rich foods, such as milk and fish. So, does it mean that, you know, after Fukushima you shouldn't eat fish? Well, again, well, you shouldn't eat fish bones. That's just not healthy anyway. But the amount, of course, of damage it would do to you depends basically on this graph, and depends on, in particular, what happens here. So how large are these doses? So again, actually, we'll come back to Fukushima and Chernobyl. Fukushima produced measurable amounts of radiation fallout, measurable here in Berkeley by the nuclear engineering department, but apparently not me. The amounts are plotted here. This is the data collected, so in fact you can click on this website, it still has the data backed up. The amount peaked, the amount of activity peaked in March 28, 2011. That was about a week, in fact, after Fukushima accident started, after the most significant release of radioactivity in the air. You know, there was rain in the Bay Area around that time. The amount of activity was roughly 20 becquerels per liter. of rainwater. So if you were foolish enough to go outside, fill a liter, that's a quart, of volume with rainwater and drink it, you would receive, you would be exposed to an amount of radioactivity of about 20 counts, 20 becquerel, 20 counts per second. So about 20 times a second, that liter of water would be producing noticeable radioactivity. Most of it is iodine, it actually decays quickly. Some of it would be cesium, that decays slowly, and some of it would be strontium, that also decays slowly. The nuclear engineering department has measured cesium, 137, and the amounts were even smaller than in the water by about a factor of 40. So the highest activity was about half a becquerel per liter of air. So how big is it? So what is the 20, let's say you were foolish enough to drink a liter of rainwater. What is 20 becquerels? So you would be getting 20 times a second, you would be hit by radiation from Fukushima. I told you your cosmic ray exposure is one hit, one particle penetrating your pupil. I keep forgetting. Penetrating your pupil every minute, or the area on your tip of your finger is about a square centimeter. So every minute, something hits you in the area of a square centimeter. You have a lot of square centimeters in your body. In fact, the typical area, well, roughly speaking, 2 meters tall, I wish, by, say, half a meter wide, is a square meter is the typical order of magnitude area of a human. That's 10,000 square centimeters. So if you multiply 10,000 square centimeters by 1 per minute, you get 10,000 cosmic ray particles hitting you every minute. Divided by 60, well, we'll call it 100. 100 times a second, you're getting hit by cosmic ray radiation. And that gives you a rate, a radiation dose of something in the neighborhood of 10, 20 millirem, if I remember correctly. So some fraction, about 10% of your normal radiation dose. The rest comes from radon and medical procedures. So, 100 times a second you'll be hit by radiation. So compared to that, Fukushima was only 20% of that. And only if you went outside, collected a liter of water and drank it. If you buy French Bordeaux, that gives you about 1 becquerel per liter of a French Bordeaux. So if you, buy 1965 Bordeaux and drink it, as I said, it probably will be a nice experience for a while, but not the next day. You'll be getting 1 extra count of radiation per second, compared to, again, 100 per second from cosmic rays. It's a small amount, relatively speaking. Is it dangerous? Well, you have to judge for yourself based on this data. And the only thing we can tell you is that we have 2 hypotheses, and we cannot really tell the difference. Even if you take the most conservative hypothesis and assume that there's no threshold, you can compute the extra risk. And then compare it to your other risks, like comparing, for example, to a risk of drinking a liter of Bordeaux and driving. That's probably going to do more damage to you on average, so will increase your probability of bad outcomes compared to radiation. So every life decision has a consequence. You need to know the chances numerically. Okay, so let's talk about some of these accidents. I'll actually come back to it when we talk about the nuclear power next week. I'll actually tell you about what actually happened in Chernobyl. But these two, the Chernobyl accident and the Fukushima accident, are the 2 most famous, for now, incidents of accidental release of radiation in the air and in the water from nuclear power. There were actually 2 others that people don't know about. There was one in 1950s in the Russian nuclear fuel processing plant called Mayak. Nobody knows this because Mayak, until very recently, has been a secret town. but they had a radiation release there in 1957. Many people died. It was a weapons facility. It actually still is. It processes spent fuel. Chernobyl is famously known. So what happened in Chernobyl is a meltdown followed by a explosion of hydrogen gas due to the overheating of the reactor, and we'll talk exactly about the mechanisms that led to it next week. From the point of view of today, what's important is the biological effects. The most terrible thing that happened was to firefighters who were trying to fight the fire. In fact, you can see this. These are graphite blocks. The graphite is used as a moderator in the reactor. So these are part of the nuclear reactor core that are just laying there on the ground, laying there on the roofs of the building. Firefighters didn't know about it. They went out to put out the fire. They were called into Pripyat, the little town where the power plant was located, to fight the fire, and they did. About 240 of them fell sick, and at least 31 of them died from acute radiation sickness, acute radiation poisoning. People actually, again, it's a terrible way to go. It's not instantaneous, so people get sick relatively quickly, but they can still talk. So these guys were interviewed about their experience, basically on their deathbeds. They reported kind of tingling sensation. They reported metallic taste in their mouth when they were fighting the fire. As far as I can tell, this is basically caused by such a large amount of radiation that it ionizes enough of your saliva that you can kind of taste it. Sort of similar, the taste is similar to what you taste if you lick a battery. But if you take a 9-volt battery, lick it, it's safe. You feel tingle and you feel kind of a metallic taste. I've done it when I was a kid. So it's sort of very similar sensation. It's basically these guys were receiving such a large amount of radiation, they were next to parts of the reactor core, that this was actually immediately noticeable. There were about 216 non-cancer deaths. This is basically either from stress, again, the emergency workers and the power plant operators. There was at least one case of suicide from the person who felt responsible. Clearly, the most, in terms of the actual raw numbers, there's an estimate based on this linear null threshold hypothesis that up to 25,000 cancer deaths were caused by the exposure, long-term exposure to radiation. And the reason that there's a large uncertainty is because it's very difficult, again, to identify this and attribute these incidents or the actual deaths to radiation exposure from Chernobyl. Some of the radiation exposure could be, in fact, detected. So there was about 6,000 cases of thyroid cancer detected in children primarily who are more susceptible after the Chernobyl accident over the next 20 years. As it turns out, luckily, at least thyroid cancers are 95% treatable. At least the survival rate is about 95%. So even though about 6,000 cases were detected, relatively few people, only about 5% of those cases were lethal. But the overall effect on the population was, in fact, enormous. The area is still off bounds. There aren't, there's barbed wire around, despite of what you see in, what's that silly movie with Bruce Willis, Die Hard 5? Despite of what you've seen in Die Hard 5, which is incredibly silly from physics point of view. These guys walk into a room in Chernobyl, they open the door, and some sort of gases and vapor spews out, and the smell says, smells like radiation. It's been cooking up here for 20 years. And then they open some kind of aerosol spray it around, and the radiation is gone. I would like to get that aerosol. Radiation doesn't work this way. It's not a chemical. It is a radioactive decay of a nucleus. You cannot get rid of it by spraying some aerosol. You have to either wait it out or shield against it. But the truth is that the area is still off limits, about, I think, at least 5 kilometers around the area. And people in the immediate vicinity, all the way to Belarus, that's at least 100 kilometers away, were evacuated. It's about 130,000 people. And up to, in the total, about 50 million RAM person exposure was received. So now you can divide this by 2,500 RAM, and that is what the estimate is of extra cancer cases, extra cancer deaths. It's this number, which is an estimate, has an uncertainty of about a factor of 2, divided by about 2,500 RAM per 100% increase in cancer rates. This is the map of the exposure. In fact, well, I actually remember this very well. This was 1986. I was 13. In fact, this is a zoom in onto the area. I lived in Leningrad, St. Petersburg, now it's known. This is end of April 1986. We went on a trip with school. Went on a trip to this town of Lviv in Ukraine. This is Chernobyl, this is Lviv, this is Leningrad. Actually, it turns out a friend of mine was also, well, a friend of mine who's now a friend of mine. I didn't know him at the time. We met in college. He's also from St. Petersburg. As it turns out, as luck would have it, he was in Kiev at the time. He was also on a school trip. You know, St. Petersburg is kind of cold and damp in the spring. It's nice to go south for a spring break, which we did. So he was a little bit less lucky. He was in Kiev. That's 150 kilometers away, I think, something of that order. He had to be, they jumped in the train and went back to St. Petersburg very quickly. In St. Petersburg at the time, around May 2nd and 3rd, people already knew about the accident. Everybody who came on these trains from the south had to be screened for radiation exposure. He says that he went to a technician facility. They took a Geiger counter, and they started counting. Sort of, sample the shoes, sample the clothes, and the thing basically went nuts. Kind of sounded, okay. I'm not sure why my Geiger counter is not counting. Well, his Geiger counter was counting. He said he had to get rid of his shoes and bury them in a little shallow grave somewhere. Didn't see them again. I was a little bit more lucky. I was in Lviv. This is the pattern of the radiation exposure around the area, primarily given by prevailing winds. Winds were blowing kind of northeast. In fact, Soviet Union at the time was a secretive country. This accident was around May 1st. May 1st, as you may have heard, it's called May Day. It's a holiday in Europe. It was a big deal in Soviet Union. It's a communist holiday. Everybody on May 1st goes outside and parades. It's sort of like the July 4th parades in this country. We all had to go outside and wave red flags and sing songs and whatever. Accidents around May 1st are kind of inconvenient for the state. So the government didn't tell anybody. The government didn't tell anybody even outside. The first time the radiation was detected was in Sweden. There was a power plant in Sweden, a nuclear power plant, and the workers at that nuclear power plant started getting radiation alarms. They thought, bummer. We must have an incident at our site. They looked around, there was no leakage of radiation in Sweden, no leakage at the power plant, and they figured out that the exposure comes from the rain from the outside. So I live actually near St. Petersburg, about an hour away. We have a nuclear physics institute there. On April 28th, people at that nuclear physics institute at the nuclear reactor in the institute started getting radiation alarms too. In fact, one of the guys went to run in the park outside, came back through the radiation scanner, and it tripped. So we basically learned about this not from the state media, but rather from the scientists in the institute. Nevertheless, everybody was still ordered outside on May 1st. Children had to, parade and wave red flags, and it was awful. Even in Kiev. I mean, in Kiev, people thought, well, we're kind of close. Should we cancel May Day parades? No, you cannot cancel May Day parades. So people still got exposed because of the basically lack of information and lack of action until the rest of the world community and the rest of scientific community in Russia actually put enough pressure on the state to release information. Information was released at the time as a news bulletin for about 30 seconds. I actually have a clip somewhere or a YouTube video of the announcement about what happened. The announcement basically says, there's an incident in a nuclear power plant, we are taking measures. And again, we'll talk about this more, but a relatively large area was affected. Now, the most interesting thing, actually, well, there were up to 25,000 deaths from cancers integrated over the last 20 years. There were a relatively large number of non-cancer deaths from stress. The Soviet government actually had a point. And this is something that I would like you to actually discuss in the discussion sections. At least the official party line about not releasing information was so that the incident would not cause panic and people trying to run out of the neighboring cities like Kiev, which they thought would cause more harm. If the city is not prepared for quick evacuation, people will just jump in their cars and drive out. There will be accidents, probably more than 100 deaths. That's actually an interesting point. I guess Japanese authorities had a very similar reaction to Fukushima. They did not release information right away either, of a fear of inducing panic in Tokyo. And so this is actually a very interesting policy decision about how to handle information, how to handle public safety. You have to trade off cause potential effect of a panic and mass evacuations against the more immediate danger from radioactive fallout. And this is what I would like you to discuss at some point. So let me stop here and we'll talk about nuclear power next week.